So to prove this step, we basically will start out with a preliminary fact, which we will prove first, and that we call proposition 1. So what does this proposition say? We can read it in detail, but remember that what we are trying to now do is to estimate the f hat terms by their approximate forms f tildes in an efficient way. So given access to randomly chosen examples from the oracle that we talked about in the form x, the input value, fx, the function value, because remember, this entire exercise is about determining fx because we don't know what it is. From us, it's a hidden function. So what we are trying to do is to use this little insight we get from x, fx, and the algorithm itself, which we will study in a future topic, the concept of randomization in detail, is a randomized algorithm, which means it tosses coins as it makes decisions. And we'll show that it can be constructed, which takes input as inputs, the set S, and for some delta value and epsilon value that you give me, outputs f tilde, so that the difference between f tilde and f hat is less than or equal to epsilon with probability at least delta. So that's the first part. Furthermore, its running time is polynomial in n 1 over epsilon and the log of 1 over delta. Okay? So these are the basic parameters that we want, and later on we will see that it's fairly easy to conclude that that would be a polynomial time algorithm in the parameters that we do care about. So in order to prove this, there are some parts of it which I'm going to leave explicitly and I'll mention to you as an exercise that you will be working on so that you'll get a firm understanding of the proof, which is important. But I'll go through the main steps other than some very fine technical calculations, which we will be discussing but leaving for out of the lecture time exercise work for you. So let us remember that we have already seen in the previous lecture that f hat x can be written as the expectation of x taken as an average of fx times x sup s. We have already seen that. So the flip here that we did, and I discussed this in the previous lecture, is you can think about estimating f hat from f instead of the normal way of thinking about estimating f from f hat. And we talked about using that idea to compute f tilde, and now we're doing that. So we are given examples, x and fx, x chosen uniformly, and using these we can compute fx times x to the power s, which will belong to either be -1 or +1, and ultimately get an empirical estimate, experimental or by running estimate of this expectation. But the question is, how many of these examples do we need? Because ultimately to get a completely precise form of f hat, we need many, many examples. So how many estimated examples do we need to get a good estimate? This means the error bound is within epsilon, and your quality is true with high probability of 1 minus delta. To do this, we have to rely on something which is very technical. From the previous lecture on the foundations of probability, I described to you something called a Chernoff bound. We've derived that in class, so I'm going to now restate that very quickly just to remind ourselves, but we will be using that result. So what was the Chernoff bound, which we are now going to use? So Chernoff's bound gives us a way to bound sums of independently distributed random variables, which are identical, usually 0 and 1. And so one form of the theorem would say, if you're given x1, x2 through xn, and they're t independent random variables from the interval 0 to 1, and let x be the sum of these random variables divided by t, and mu be the expected value. Okay? Then the bound says that the probability that x is bigger than mu, or the distance between x and mu is bigger than epsilon, I misspoke, sorry. The distance between x minus mu is bigger than epsilon, is less than equal to this form. And that was something that we already stated. So now we're going to sketch out to you in the next 5 to 10 minutes a way of applying this bound to be able to determine how many examples we need in order to be able to satisfy both epsilon and the quality criteria delta. So what in particular we are setting out to show is the number of examples which I mentioned earlier on, m, is no more than 1 over epsilon square log 1 over delta to satisfy, to be within an epsilon of what you want and with high probability of 1 minus delta. So this is something that we'll work out, as I said, in a detailed exercise, but I wanted to take a few minutes to walk you through the main steps of how we would solve it, leaving some intermediate steps out. So what I call a hint here on how to solve it is first to note that fx times x sup s is either minus 1 or 1, an observation I made earlier on, which you might have taken for granted. First thing to try to understand why that's true. It kind of forces us to think. It's not hard, but it requires a few minutes of thought. And now let us write the symbol y to be fx times x sup s. And then the second observation I want to make is, and this is something we stated earlier on, expectation of y is what f hat s is. So if I could do this entire expectation, we're in great shape. We're trying to estimate it, right? Now let y prime be 1 minus y divided by 2. Just an algebraic step. Okay? First observe, few minutes of work, that y prime is either 0 or 1. And now we apply the Chernoff bound in the previous slide to actually calculate the number of examples, and that takes a little bit of work, worthy of an exercise. So I'm not going to spell it out and show you the calculation because it's, at this point it's fairly mechanical, but it forces us to think about why this works. So I said there were two things. What I have now shown is, as a function of epsilon and delta, how many examples we need. What's remaining now? What does it cost us? How much running time will our algorithm take with those many examples? And that's what I'll now walk through. So I'll do a quick algorithm analysis of what the complexity is. So we already are implicitly saying that when we have an oracle, it takes constant time, practically doesn't cost us anything, big O of 1 to be specific, to get an xfx pair back. That's the first premise, because the statement of the theorem asserts the existence of such an oracle. So in that sense, this is a conditional theorem. We will later on see how to deal with that condition. So what we want to show is, with this oracle helping us, the running time is polynomial in n, 1 minus epsilon, times log of 1 over delta. So since we assumed constant time for each example, basically if we want, from the previous assertion, the exercise that I mentioned, this many examples, 1 over epsilon square times 1 over delta, that is the amount of time we need in the big O sense for all the examples, correct? So that's the amount of time we need in terms of just reading out the examples. For each such sample or example, xfx, fx ss can take linear time, something you can easily work out, to actually compute this product. Because fx takes practically no time because it's given to you, but that multiplied by x sup s is basically linear time. And now, so it takes linear time to do this many examples. So what you have is the term n multiplying this, because you do that n times. So that's n divided by epsilon square times log 1 over delta, which rewritten another way is simply a polynomial in n 1 over epsilon times log 1 over delta. So that's just simply another way of writing this expression, which tells us what the total running time is. And that is what we set out to prove as our overall running time for this proposition. So that's a good point to pause for a few minutes, think about what we have learned before I will start again with proving now the second step that I mentioned as a way of building up to the complete proof.